with like what solutions are. By the way, this is chapter 9 is where it is in your book if you want to reference it. So do this here, disconnect. Okay, so first off, a solution is a homogeneous mixture and if you remember, homogeneous means that everything mixes right, everything looks the same throughout. And a solution is actually the formulas and stuff that get the AQ symbol. So AQ means aqueous. It means it's sort of a water environment. And a reminder that there is a difference between aqueous and, again, the sort of L symbol, which is liquid. Something that gets the L symbol is just a pure substance by itself. So again, if you had something like just water by itself, that would get a liquid sort of designation. If you take something like water, which is a pure liquid, and you actually mix it with something else, say like some sodium chloride, solid sodium chloride, which is just some salt, the sodium chloride or the salt will dissolve in the water, and you will end up with a sodium chloride solution that will get the aqueous symbol. So that aqueous symbol basically represents a solution. Pretty much all the little bottles that you use in the lab that have the reagents in them, they're basically solutions. They're aqueous type of solutions. The good news is the name of the solution is also really what is dissolved in it. So like in this case, this would be a sodium chloride solution. That's basically much what's dissolved in it. So when we do have a solution, there's actually two parts to a solution. There is two parts. One part is what is known as the solute, and that is the smaller part of the solution. The other part of the solution is the solvent, which is the larger part of the solution. So basically, when you take the solute and the solvent together, you make a solution. In our example over here with the water and the sodium chloride, the water here, which is the larger part, would be our solvent. And the sodium chloride here would be our solute. So in addition to the name of it here, the name of a solution is always going to be the solute. So if it's a sodium chloride solution, it's sodium chloride is what's mixed in there. If you had a potassium chloride solution, then it would be potassium chloride would be in there. So whatever the name of it is, and it has like the aqueous symbol next to it, that is always going to be the solute. Water, for the most part, is a really good solvent. It's not always a good solvent for all things, but it is a good solvent for a lot of things. Because water is polar, if you remember, there is a negative side to water, which is the oxygen. There is a positive side of the water, which is really the hydrogens, and that's because it's a polar molecule. So when you take, for example, something like sodium chloride, what happens when the sodium chloride goes for a swim in the solution, or the water basically, is because it's ionic, it will break apart into its ions. And what ends up happening is these ions get pretty much surrounded by water. And so, for example, the sodium ion, which is positively charged, will get surrounded by the negative oxygen side of water. Remember, opposites attract, so the negative side of water there would be attracted to the sodium ions, while the positive side of water would actually be attracted to the chloride ions, and that would be the hydrogen side of water. And what this actually does is it's pretty much how this thing dissolves. The sodium chloride really doesn't go anywhere. It doesn't sort of react with anything. This is actually a physical change that's happening when you make a solution. We just visually cannot see it anymore because it's surrounded by a ton of waters, basically, and it's no longer visible to us, the solid that went into for a swim. So all these ions basically get surrounded by all these water ions. It does two things. It allows the sodium chloride, for example, to dissolve and make a solution. It also prevents the sodium ion and the chloride ion from coming back together, which they definitely would want to do because they're attracted to each other. But the water almost acts like a buffer, so they can't get back to each other. So it kind of prevents them from coming back together. We know that, this is sort of a physical sort of change, and nothing really happens to the sodium chloride because I'm pretty sure you've done it or will do it. If you take this and basically start heating it up, right? What's going to happen to the water molecules? They're going to start to evaporate, right? So all the water molecules are going to start to evaporate. And now there will be nothing left to keep the sodium ion away from the chloride ion. And when you evaporate off all the water, those two guys will come back together, and you would have, like in your dish, some sodium chloride solid that would come back after you evaporate off the water. So the process of making a solution happens when we mix things that are very much like each other. They interact the same way. So water, which is sort of polar, has a positive negative side, is able to interact really well with something like sodium chloride that also has sort of positive and a negative guy. Now, for example, if you try to use water as your solvent for something like chlorine, right? And just from our Lewis structure of chlorine, looks something like this. Chlorine is a polar or non-polar molecule? Because they are both chlorine here, the difference in electronegativity would be 0, which means this would be a non-polar molecule, basically chlorine. So chlorine, when you have chlorine, it's basically neutral, has no charge, which means when water comes by that is negative and positive, it has no way to sort of interact with each other. So those two things would be really bad to put together because they have no way to interact with each other. Something like chlorine or something like that that's non-polar would need another non-polar solvent to be used. So maybe like carbon tetrachloride, which is also non-polar. Those two guys then would mix really well, or hexane, which is also non-polar, and stuff like that. So water is a lot of times the solvent that's used, but not in 100% of its cases is it really good. When we talk about things mixing and solutions mixing, sometimes the terminology of like dissolves like. And what that means is if you have a polar thing and a polar thing, they're going to mix really well and sort of mix together. If you have a non-polar guy and a non-polar guy, they also will mix really well and be fine together. If you have an ionic guy, like we did with the sodium chloride, and a polar guy, they also will mix really well together. So these three combinations of things will be really well. They'll mix. There'll be what is referred to as being soluble in each other, and they'll mix really well. So only when you cross over like polar and non-polar, that is going to be a no-go. That's going to be insoluble in each other. They really will not mix really well. And the real reason is they're both trying to use different types of way of interacting. So they don't have the same way to interact with each other. So they can't really mix really, really well. But anything that's polar and polar are going to interact with each other the same way they interact with themselves. So they're going to be able to mix really well. Anything that's non-polar will also be able to interact the same way they interact with themselves. So they'll be able to mix. But when you cross over something that's polar and something that's non-polar, they just don't have that way to continuously interact with each other. Like, for example, oil and water, right? Whenever there's an oil spill, right, the oil ends up floating on top of the water, right? Because there's no way for those two to interact really well with each other. Oil's non-polar, water is polar, so they're not able to interact very well with each other. Remind me later again. All right, thank you. All right, so when we talk about solutions and things mixing together, sort of that idea of if you could identify as the two things you're mixing are polar and polar, they're definitely going to mix. Non-polar, they're going to mix. But again, if you cross over polar and non-polar, not going to have some great mixing going to occur. So when we talk about solutions as well, we also sometimes talk about electrolytes, which I think is a topic of the first lab, maybe. Electrolytes. And electrolytes are things that when they break apart in solutions and form ions. So these are things that when they go for basically a swim in water, they break apart into ions. And because they break apart into ions, it's really important for it to be able to conduct electricity. So there's couple of types of electrolytes. The first one is a strong electrolyte. And a strong electrolyte will 100% break apart into ions. So for example, if you had a sodium chloride solution, in the actual solution, the only thing that you have really floating around, like in that beaker, are the sodium ions and the chloride ions. 100% of what you have in that solution is just the ions by themselves. There is no sodium chloride unit still together. They have completely broken apart. Because they have completely broken apart, you could think about it like a one-way street. It's all just going to dump out on the product side into ions. It makes a lot of ions really quickly, and strong electrolytes conduct electricity really well. A very common experiment is they take a light bulb, which I'm just going to draw as a square because I've tried to draw a light bulb before and it didn't look right. And that light bulb is hooked up to a couple of electrodes. And when they put that light bulb, the electrodes into a strong electrolyte solution, it will go off very brightly. So it'll be very, very bright. The light bulb, because it's able to conduct electricity, is the presence of all those ions, which help kind of complete the circuit and allow electricity to flow very, very well. Now, different than that is a weak electrolyte, and a weak electrolyte will mainly stay together. But will produce a few ions. And for example, hydrofluoric acid is a weak electrolyte, also a weak acid. It breaks apart into H plus and F minus. Now, in this particular case, what you mainly have in the solution is actually HF. So you mainly have floating around in there HF molecules still together, not separated, still together. But you do produce a little of these ions. So in addition, you got some H pluses floating around, you got some F minuses floating around as well. So because it's still able to produce a little bit of ions in the solution, it actually is also still able to conduct electricity. So it will conduct electricity if you take your light bulb, and you'll probably see this thing next week. It looks like it's been here since the 60s and going to electrocute somebody. But when you take the light bulb here, it's going to turn on, but it's going to be very dim. So it's still able to conduct electricity, but nowhere near what a strong electrolyte can do. So light bulb will turn on, but it'll kind of look like it's dying. It's kind of dim and stuff like that, because there still is a few ions produced, but mainly a weak electrolyte will actually stay together as the whole units and produce a little bit. How can you tell the difference between the two besides the results of your light bulb experiment? Clearly, if you do the experiment next week and the light bulb is very bright, that is a strong electrolyte. It should all break apart. If you do it and it's dim, it's a weak electrolyte. But it's actually the arrows. In a strong electrolyte, you have a one-way arrow, which means everything is going to the product side. Everything is dumping out and becoming ions. In a weak electrolyte, you typically have these arrows heading in both directions. So you have this sort of reversible arrows. So you got guys going this way, and this is what is sometimes referred to as the forward direction. And going from reactants to products is what is sometimes referred to as the reverse direction. And that is typically what you see in a weak electrolyte, are those arrows. And what ends up happening is the forward direction from reactants to products will occur, but at some point you'll make enough products that they will decide we want to go back the other way, and they'll kind of come back the other way and make some more reactants. And that definitely is a weak electrolyte. So if you have an equation given to you and you see the arrows heading in both directions, that is definitely going to be a weak electrolyte. If you see a one-headed arrow or one-way arrow heading to the product side, that's most likely going to be a strong electrolyte if you have ions on the other side, obviously in each of these cases. Any questions on that there? Now, a non-electrolyte is something that actually will dissolve. So we can have a non-electrolyte. And that is something that will dissolve in solution, but it will not create any ions. So although it will dissolve, there will be no production of ions. So for example, if you took sugar, right, and you put it in water, you could get some sugar that dissolves, obviously. But sugar is basically carbons, hydrogens, and oxygens. So it's all covalently bonded, sharing of electrons, no ions. So because we don't produce any ions here, if you took your light bulb example there, not turn on, yeah. So will not conduct electricity. Again, because of the lack of no ions, no electricity, basically produced. So how you could identify sort of in a book, an equation that it represents a non-electrolyte is when you look at the equation, you have the same thing on both sides, basically, and no ions on either side. And that would be a non-electrolyte, and you wouldn't expect it to conduct electricity. Question on that there. Pure water is a bad conductor of electricity. Yeah. So if you have just H2O, because there's no ions in it, it is actually a really bad conductor of electricity. Safety warning, the water that comes out of your pipes is not pure water, so you will electrocute yourself if you blow dry your hair while you're taking the shower. They actually put ions into your water to clean it, so there's lots of ions in your water, which is why you can get electrocuted, obviously, with water that comes out of your pipes. But if you have just pure water, just H2O, it's actually a bad conductor of electricity because it doesn't have any ions that are present. Any questions on electrolytes? So to sort of quickly identify electrolytes from equations, what you would look for a strong electrolyte is an ionic compound on the left, ions on the right, and a one-way arrow. For a weak electrolyte, what you would look for is an ionic compound on the left, ions on the right, and double-headed arrows heading in both directions. And for a non-electrolyte, what you would look for is really the same thing on both sides, just one was solid and one dissolved, and a one-way arrow. You would identify that. And again, strong electrolyte, very bright light bulb, weak electrolyte, dim light bulb, and non-electrolyte, no light bulb goes on, is basically dark because no electricity conducting. Any questions on that there? Okay, so let's talk a little bit about a couple of concentration units, which I think might be in that one too. I'm not sure, but we'll try. Concentration units. So a very common concentration unit of solutions is one is percent mass to mass, or mass to mass percent. And that is the mass of the solute, which is the smaller part of the solution, divided by the mass of the solution times 100%. So that is basically what percent mass to mass is. So for example, if you made a solution by mixing 32 grams of sodium chloride with 125 grams of water, you know, what is the percent mass to mass percent? And again, that is sometimes referred to as mass percent. So to do this, we want to figure out a couple of things. First off, the percent mass to mass in this case would be the mass of the solute divided by the mass of the solution times 100%. So when we look at what was given to us, we have two things basically given to us. We have the sodium chloride and we have the water. In this case, which one would be the solute? The solute is the smaller part of the solution, so it would be the sodium chloride, right? That's the smaller part of the solution. So that guy right there would be our solute. The sodium chloride would be our solute, and our water here would be our solvent. So the mass of the solute in this case is pretty simple. It is the 32 grams, right? Now, the mass of the solution is the important part of this calculation. There are two parts to the solution, right? There's the solute and the solvent. So when you do these type of problems, you want to make sure you get the mass of the solute plus the mass of the solvent, which means in this particular case, the mass of the solute is 32 grams. The mass of the solvent is 125 grams. So we actually need to add those together to get the mass of the actual solution. So that's going to be 32 plus 125 will give us 157 grams. What most people do when they do this type of problem is they actually just take the solvent by itself, and that will not get you the solution. So the bottom part is the solution. So you got to make sure that you get the solute and the solvent added together, because historically in these type of problems, they are given to you separately. So they'll give you the solute separate from the solvent's mass. They won't just straight up give you the mass of the solution. So a lot of times you do got to make sure that you add those two together. At this point, we have everything we need if we wanted to calculate it. Our percent mass to mass would be our mass of our solute, which is 32, divided by the mass of the solution, which includes both the solute and the solvent, and we'll times it by 100% here. And in my made up example here, we end up with, not that, 157 times 100. End up with 20.4%, and most people will leave it M/M and also put maybe sodium chloride, as that is the solute in this case, would be our mass to mass percent question on that type of concentration unit there. Now, if you're given sort of the percentage of the solution by mass, you could kind of convert it into a conversion factor and use that as a conversion factor to sort of solve a problem. So for example, if we were told that we had a, say, 7.5% by mass sodium chloride solution, we could actually turn that into like usable conversion factors. And we could do that because this is a percentage. So a lot of times if we want to convert a percentage into a usable sort of number, we should assume that we have 100 of it, right? So it makes the numbers all stay the same. So for example, if we did have something that said, hey, we had a 7.5% by mass sodium chloride solution, what that would mean is there would be 7.5 grams of sodium chloride in 100 grams of solution. So you could kind of turn that into a sort of conversion factor. You could also use it the opposite way around. 100 grams of solution is 7.5 grams of sodium chloride in this case. So this would be useful, for example, if we had something that asked like you had 525 grams of solution, how many grams of sodium chloride were there? So in this case, we could take the 525 grams, and since we already turned our percentage into conversion factors, we have 525 grams of solution. Once again, thinking of it like a dimensional analysis problem, we would want the solution on the bottom so it cancels. And if we do that, that would be 100 grams of solution is 7.5 grams of sodium chloride. The grams of solution will cancel, so that'd be 525 times 7.5 divided by 100 gets me 39.4 4 grams of sodium chloride would be dissolved in that solution. So this is one way that you could take the percentage and solve it sort of a dimensional analysis way. You also, if you wanted to, could just plug and chug into the original equation. And in this case, we were given the percentage. We were given the mass of the solution, so you could just rearrange and solve for the mass of the solute, which is the exact same math we did above. So if you wanted to, you could just plug it into that equation too and solve it. Or you could kind of turn the percentage into a conversion factor and kind of do it more dimensional analysis approach. They both give you the same answer, and it's really the same math, no matter which way you kind of do it. Any question on percent mass to mass? So the key on that one is to make sure that bottom part there, that you actually get the entire mass of the solution, not just the solvent, which is again a very common mistake that people make. Another really more common unit of concentration is molarity. And molarity is abbreviated with a capital M, and molarity is moles of solute per liter of solution. Although most people just call it moles per liter, basically. And you could think of this like a formula that you can actually rearrange it and solve for a bunch of stuff. You could solve for liters. Liters would be moles divided by the molarity. And if you wanted moles, it would be liters times the molarity. So there's a few different ways that you can rearrange that equation to solve for it. When you're given the molarity of a solution, like if you had a 6.5 molar sodium chloride solution, I highly recommend the big M and replace it with both units, the big M, and they go and do sort of the math part of it. Is they have no idea where the liters is or the volume is. So it's a really good idea to turn something like that into 6.5 moles per liter. That way you could clearly see the moles, you could clearly see where the liters are, and that would be a good way to use it. You could also use it like a conversion factor as well. You could put the liters on top and 6.5 moles on the bottom. So again, you can kind of use it dimensional analysis ways, so you could kind of see all the units. So for example, if I had 16 moles of sodium chloride and I want to know how many liters that was, and maybe milliliters that was, I could use my molarity to help me do that. If it is this molarity here, we'll use that molarity. And I could just use the equation and go, all right, well, I got moles given to me and I got the molarity given to me, so I could solve for liters. That's the only thing I don't really have. Liters here would be moles over molarity. So I would take my 16 moles of sodium chloride and I would do it like a dimensional analysis. And I would use my conversion factor here on the right so that the units cancel. I would put liters up on top, which is what we're looking for. 6.5 moles on the bottom. And again, that comes from the molarity of the solution that was given to us. The moles here will cancel, and that would give me 16 divided by 6.5. Gets me 2.46 liters of sodium chloride, which probably should be like 2.5 on some significant figures. One very important conversion with solutions is liters and milliliters. There is 1,000 milliliters in a liter. So that's a conversion that you use a lot with solutions. So if I did want milliliters here, 2.5 liters, and we'll do our conversion. 1 liter is 1,000 milliliters. And that would give me 2.5 times 1,000. 2,500 milliliters of sodium chloride. So if I knew the moles and I knew the molarity, I could use it to figure out the volume, either liters or milliliters, which is a very common sort of unit. Question on that there. Now, if I wanted to just calculate the molarity of a solution, basically all I need to get is those two units. I need to get the moles of it and the liters of the solution. So if we were to actually just want to calculate the molarity of it, let's say we were going to make the sodium chloride solution. So we decided to dissolve 5.55 grams of sodium chloride in enough water to make 325 milliliters of solution. So here we actually want to calculate what the molarity is here. So once again here, the molarity is moles per liter. So really what we need to do is get both of those units. And in this case, I have grams of sodium chloride, which by the way is my solute, right? And my water here is my solvent. If I need to go from grams to moles, we use the molar mass like we did today, right? So we're going to do that conversion. We would need the molar mass of sodium chloride, and that would be 2299 grams per mole for the sodium from the periodic table, and 3545 grams per mole like we did today for the chlorine from the periodic table. Gonna give us 5844, I think, maybe. Going to get us 58.44 grams per mole. So just like we did today, the first part of this calculation will just be a simple conversion between grams to moles like we did. So we'll start with that. That's going to be 5.55 moles of sodium chloride. Using our molar mass as a conversion factor, we're going to do 58.44 grams per mole of sodium chloride. The moles will cancel. And that's going to give us, excuse me, I did it backwards there, sorry. We actually had grams. Let me get the right units there. Well, that number seems a little bit big. Excuse me. All right, we actually had grams of sodium chloride. There we go. Start with the right units would be good. So we are going to put the grams on the bottom there. That would work much better. And moles up on top. Get a much decenter number. Our grams now will actually cancel, and we're going to take 5.55 and divide it by 58.44. And that's going to give us 0.09497 moles of sodium chloride. So when I think about my molarity, I just calculated the moles part. So what is left that I need is the liters part. And that's going to come from my milliliters here, right? So there's a solution. So we need to convert our milliliters of solution into liters of solution. So once again, there's 1,000 milliliters in a liter. The milliliters will cancel. We'll end up with 0.325 liters, which is the bottom part for what we need. So now we have everybody in the right units. To figure out the molarity, we're just going to divide the two. So we're going to take the moles, which is 0.09497. We're going to divide it by the liters, which is 0.325. And we will end up with here 0.292. Now the units here do not cancel, so the number always stays with the moles. And it's always per 1 liter. So you could leave it like that, or you could write it 0.292 big M. So you could do either one. The big M stands for moles per liter, and you could write it either way as your answer. So if we made the solution by dissolving that 5.55 grams of sodium chloride in enough water to make that much solution, the molarity of our solution would be basically 0.292 molar. Any questions on that calculation? Okay, last thing here we'll talk about then is, I think, the other thing that might be in that first one, which is equivalence. Now, equivalence is I don't know, a funky way to do concentration units. Sometimes equivalence, we look for equivalents per liter, or sometimes milliequivalents per liter. And this is sometimes the concentration that we see like in IV bags. So it's been a while, but years ago, they used to make you look at IV bags and sort of look at these sort of units, I think. So these are two common sort of units of equivalence, but what equivalents are, they're really related to the charge on ions. So they're basically based on ions. So they're related to the actual charge. So for example, if you had a calcium with a +2 charge, you could actually come up with a conversion factor that says for every 1 mole of calcium with a +2 charge, you actually get 2 equivalents, and it comes from the actual number. So it has nothing to do with the positive or negative. It's just the actual number tells you how many equivalents you would have. If you had an iron with a +3 charge, 1 mole of iron 3 would have how many equivalents? 3 equivalents. Again, the actual charge. If you had sulfate, which is -2, 1 mole of sulfate would have how many equivalents? 2. And again, it doesn't matter if it's positive or negative, it's just the number. Yeah, it's basically that. What we use these sort of guys for is to kind of convert concentration from, say, molarity to equivalence and stuff like that. So for example, if we had something, since we just talked about molarity, that was, say, we'll do 0.25 molar calcium ions. And that basically is the same as saying 0.25 moles per liter of calcium ions. And if we wanted to basically convert that into equivalents per liter, we could use basically that as a conversion factor. So for example, if we took our 0.25 moles of calcium ions per liter, I ultimately want to end up in equivalents per liter, which means the bottom unit is already good. I don't have to do anything to the bottom unit, right? But the top unit needs to go from moles to equivalents. So we would look at our charge and go, okay, that is basically the relationship, which means, again, we could write 2 conversion factors. 1 mole of calcium is 2 equivalents. Our 2 equivalents is 1 mole of calcium, right? So in this case, since I have moles of calcium up on top, I would want moles of calcium to be on the bottom so that they cancel. So we would use the conversion factor here on the right, and that would give me 2 equivalents per 1 mole of calcium ions. The moles of calcium ions will cancel. We'll get 0.25 times 2 gives us 0.5 equivalents per liter. So we now have converted into really just another sort of concentration unit, which is equivalents per liter. And if I wanted milliequivalents, milliequivalents is the same thing as like milliliters and liters. So there is 1,000 milliequivalents per an equivalent. So if we wanted milliequivalents per liter, you would just do one more conversion, where in 1 equivalent, there is 1 milliequivalent. It's really the 1,000 milliequivalents. So it's really the milli conversion, which is 1,000, and we would have 500 milliequivalents per liter. So sometimes we use the charges to get really just a conversion factor between moles and equivalents. And in most cases, you're just going to use it to kind of convert from, say, moles per liter to equivalents per liter, or backwards and stuff like that. So it's just another sort of unit of sort of concentration that's used for ions because they have charges. So they sometimes refer to them as sort of equivalents per liter. But to get this sort of relationship of equivalents to moles, it is simply just the number of the charge. Doesn't matter if it's positive or negative. And again, you'll use that really as sort of a conversion factor. Any questions on any of that stuff there? Hopefully that's the stuff in your lab, I hope, right? It's going off of my memory, I hope. All right, so I hope that helps.